Hi, and welcome to the last official lesson side of this Mathematical Level 1 Algebra series that we're doing. So today we're looking at problem-solving style questions. So basically, a lot of the questions that I've got today end up being called generalizations. So that's like a mathematical proof. So we want to prove something happens. And when we do that in algebra, we write expressions and we use our algebraic rules and algebraic skills in order to sort of simplify those and show what it is that we want to show. So in some scenarios, you might start by trying out some numbers and see what happens. That often helps to give you a sort of feel for what's going on and might help you to build into that sort of generalizing process. Sometimes you might have to write an expression and then simplify that as you go through your proof. And sometimes you might need to try sort of more than one approach for these kinds of questions. So I'll just, summarize that for you again. So we're looking at generalizations, so mathematical proofs. Sometimes we might throw in some numbers, get a feel for what's going on, and then use that to build our generalization from. Sometimes you might need to try some more than one approach. You might write an expression to represent something based on the information you're given and sort of work that through. So all of the questions I'm going through today are from old exam papers. So we'll get started and I'll go through the marking schedules as usual as we go through this question. So the first one that we're going to look at is from a 2018 paper. To do with circles. So Georgia is designing a new logo for her sports club made up of two circles, and we can see those here. She draws one circle on top of the other. The total height of the two circles is always 20 centimeters. So no matter how this changes, this circle will always be drawn so that we get that 20 centimeter height. Georgia is exploring what happens to the total circumference of the two circles when the radius of one circle increases and the other decreases. And the question is asking us to show that the total of the two circumferences, so this plus this, is going to be 20 pi centimeters. Okay, so that's kind of where our proof essentially comes from. And we want to prove that no matter what the radius is for these two, we're going to get 20 pi when we add the circumferences together. And they've given us the formula to find the circumference of 2 pi r. So a little bit of information to sort of get our heads around. You might want to start with numbers. You don't have to, but you might sort of just throw in a few numbers just to see what's going on. So we're going to start with that today, and then we're going to build into our generalization. So we know that this height has to be 20 centimeters. So let's just think about these two circles for a moment. Let's say that this is 12, and because this has to be 20, then this would have to be 8. Now, if this is 12, then R1, so we'll call it the radius for this first circle down here, would have to be, this is 12, would have to be 6, half the diameter, and R2 would have to be, this is 12, so this is 8, so R2 would have to be 4. So the circumference, the total circumference, is equal to the circumference of the first circle plus the circumference of the second circle. Okay, so we can write that as C1 plus C2. So if we use our numbers, the circumference of the first circle is 2 pi times radius, which is 6, and the circumference of the second circle is 2 pi times the radius, which we said is 4. So this becomes 12 pi, 2 times 6, and this becomes 2 times 4, which is 8 pi, and if we add those together, we get 20 pi, exactly what we were looking for, okay, down here. If we take another example, so let's say the diameter is, say, 14 for this one. That means R1 would be 7. If this diameter is 14, then this has to be 6, which means R2 is 3, half of that. So our total circumference, TC, is equal to 2 pi times 7 plus 2 pi times 3, which is 14 pi plus 6 pi, 14, 6. gives us 20 pi. So we can see that it works. Okay, so we need to go a little bit further. We need to write a generalization. So instead of using numbers here, we're going to use x's, or you might use n's, we're going to use variables. So because we know that this always has to be 20, we know that this radius plus this radius always has to equal 10. Okay, so R1 plus R2 is always equal to 10. Okay, and that's because the two diameters have to add to 20. Okay, so likewise, the diameters always have to be 20. Okay, and you can use that if you prefer. So, if we want our total circumference, we take 2 pi times radius 1 plus 2 pi times radius 2. You'll see that we have a common factor of 2 pi. So if we take that out in front, we get 2 pi R1 plus R2. Okay, so we've just factorized this by taking out our common factor of 2 pi. We're left with R1 plus R2 in our brackets. But we know from here and from our diagram that R1 plus R2 is always equal to 10. So this becomes 2 pi times 10. 2 times 10 is where our 25 comes from. Okay, so this is our generalization. We've started with general terms for the radiuses, or the radii, I should say, and we've managed to simplify that down and show that it is 20 pi. You can do the same thing with the diameter. So if you're using a diameter, the circumference of the circle is just pi times diameter. Okay, so the circumference of the two circles would be, so the total circumference would be pi times diameter 1 plus pi times diameter 2, which is equal, taking out your common factor of pi, we have pi times diameter 1 plus diameter 2. We know that the diameters have to add to 20, so we get 20 pi. Either of those is fine, you certainly don't have to do both. Okay, so for this question, if you can use two different radii, so you get one here, like this, that adds to 10, and you show that you get 20 pi, that's sufficient for achieved. If you state the relationship between the two radii, so you know that they both have to add to 10 in general terms, or you state the general terms for the diameters adding to 20, that's enough for achieved, one of those. You find consistent solutions from a generalized equation. So your generalized equation is quite correct, but you can find consistent solutions from that, enough to achieve. For merit, you can do two numerical calculations. So like we did first, that would be sufficient for merit, either using the radius or you could do calculations with diameters, fine. Or you get two correct procedures from achieved. So maybe you state this and you give one numerical example, that's also enough to give merit. For excellence, you need your correct proof using either the radius or the diameter, okay, and showing your algebra as you go through that question. The second part of this question, so we're still looking at our circles, so all of this information is still the same. This part is asking us to give the equation for the difference of the areas of those two circles, the difference in the areas of the two circles. They're giving our answer in their simplest form, and they've reminded us that the area of a circle is pi times radius squared. Okay, so this area is pi times radius squared. We want the difference in the areas of our two circles. So the difference in areas, I'm just going to write dA for difference in areas, is equal to pi times radius 1 squared minus pi times radius 2 squared. Okay, so we're taking the area for the first circle and subtracting the area for the second circle. Okay, now we know from before that R1 plus R2 is equal to 10. That hasn't changed. That's still the same. Okay. We really don't want to have two different unknowns in here. So we're going to use our substitution skills that we looked at with simultaneous equations in order to rewrite this. So if R1 plus R2 is equal to 10, then R2 must be 10 minus the first radius. So we're going to substitute, instead of having R2, we're going to write 10 minus R1. Okay, so that means that our formula now becomes pi times first radius squared minus pi times 10 minus the first radius squared, because we know that this is equivalent to that second radius. From here, we want to maybe take out our common factor of pi. Pi comes out in front. We've got R1 squared minus 10 times R1 squared. Now we expand. We're going to simplify and see what comes out. So pi stays out in front, and that R1 squared isn't going to change. And we're minusing all of 10 minus R1 times 10 minus R1. Okay, so keeping this in brackets because we need to subtract this whole thing. 10 times 10 is 100. 10 times negative R1 is negative 10 R1, and then negative R1 times 10 would give us another negative 10 R1. So together we get negative 20 R1, and negative R1 times negative R1 is positive R1 squared. Okay, so we are subtracting all of this from R1 squared. Okay, so now we can simplify that. R1 squared minus R1 squared, that they cancel out. We've got minus 100, but minus 20R. So if we minus 20R, we get positive 20R1. And we are minusing 100, and we've already subtracted that. So we get pi times 20R1 minus 100. The question has asked us to give our answer in our simplest form. So we've got two options. If we expand this out, we get 20 pi times R1 minus 100 pi. Or you've got a common factor here of 20 pi. So 20 pi can come out in front. We've got R1 minus 5. Either of those solutions are fine. So you can either just expand it out and leave it, or you can factorize it fully. This is not in our simplest form because we can still factorize. We've got a common factor between 20 and 100. So we either need to expand it out or fully factorize. So for this question, for achieved, you form your equation using substitution. So you get this far. For achieved, or you consistently expand your quadratic. So whatever you end up with for your quadratic, you expand that correctly. You consistently simplify your expression, or you consistently factorize. Okay, here. So any one of those things. For merit, you do two of those things. Okay, so maybe you get this and you expand, okay, but you don't get your simplification. That was called merit. For excellence, you need to establish that relationship, and again, we accept either this or this. Moving on to a 2017 question. So A and B are two consecutive odd numbers where B is greater than A. If C is equal to B over A minus A over B, give the value of C in terms of A, and explain why this will always be an even number divided by an odd number. There's a lot of information here. Let's just maybe break this down first. We've got A and B. They're two consecutive odd numbers. So consecutive means one after the other, but they have to be odd. Okay, so we've got odd numbers, one after the other, and B is the bigger of the two. So for example, B could be 5 and A could be 3. Okay, so consecutive odd numbers. We've got this expression for C, and they're asking us to give the value of C in terms of A. Okay, so we've seen this in terms of A when we were rearranging the formula. It's kind of similar, except we're not going to rearrange it to make C the subject. C is already the subject. Okay, so what that means is that we need to write B in terms of A and then try and simplify as much as possible. Once we've done that, then hopefully we'll be able to see how we can address the second part of this question, explaining how we get an even number over an odd number. Okay, so two consecutive odd numbers. In maths, if we're sort of doing some general terms, if we have an even number, we know a number is even if it's divisible by 2. So an even number we normally represent by 2n or 2x, a, whatever variable you want to use. An odd number isn't divisible by 2. Okay, so we would say that a is equal to 2n plus 1. So if we add 1 to any even number, it has to be odd. Okay, now b is bigger than a, and it's the next, so consecutive means the very next odd number. So if a is 2n plus 1, b would have to be 2n plus 3. Okay. Now, coincidentally, b would be a, because we want this in terms of a. We maybe try and write b in terms of a. So b would be a plus 2. Okay, so if a is 3, then b would have to be 5, so we're adding 2. If a is 17, b would have to be 19, so we're always adding 2. All right, so we're going to rewrite this c, this expression for c, except instead of writing b, we're going to replace it with a plus 2, because that's what it's asking us to do, write it in terms of a. So c is equal to b, which we know is the same as a plus 2, minus a over b, which we replace again with a plus 2. So with the fraction, we're going to simplify our fraction. So it's a subtraction. We need to get a common denominator. So to do that, we're going to multiply both the top and bottom of this first fraction by a plus 2. And we're going to multiply the top and bottom of the second fraction by a. So we get a plus 2 times a plus 2 minus a times a, which is a squared, and then at the bottom a times a plus 2. So expanding out our top line, we get a times a is a squared, a times 2 is 2a, and then 2 times a is 2a, so that gives us 4a plus 4 minus a squared all over, and if we expand the bottom, a squared plus 2a. Simplifying that top line, a squared minus a squared cancels out, so we're left with 4a plus 4 over a squared plus 2a. That's as simplified as we can get. So we've done the first part of the question. We've given the value of c in terms of a. Okay, we've only got a's here, no more b's. The next part of the question is asking us to explain why this will always be an even number over an odd number. Okay, so this part here, 4a plus 4, well, we can take a common factor of 2 out. And anything that has a factor of 2 is even. So therefore, as 4a plus 4 has a factor of 2, it will always be an even number. Okay, so if you're asked to show that something is even, you need to show it has a factor of 2. The next part, a squared plus 2a. We need to show or explain why that's always going to be an odd number. Okay, so remembering that a is odd, a squared will be odd because a is odd. C-E-C-A-U is odd, and any odd number squared is odd. 3 squared is 9, 5 squared is 25, 7 squared is 49. So any odd number that you square will always be odd. Okay, so that's the first part. And then our 2a also has to be odd. Sorry, 2a is even. Doesn't have to be odd. 2a is even, because it has a multiple or a factor, sorry, I should write factor of 2, and then any odd plus even number is odd. Okay, so if a squared is odd and 2a is even, then when you add an odd number and an even number, you always get an odd number as a result. Okay, so any odd plus even number is odd. Therefore, a squared plus 2a is always odd. Okay, so that's a really full explanation. The other way, if you'd left this factorized, then you've got an odd number times an odd number. Any odd number times an odd number is also odd. So you could use the argument if you left it factorized, or the even plus odd thing if you expand it out. So for this question, a little bit going on. For achieved, you have an expression for 2 consecutive odd numbers and you substitute those into the equation. So you either get this, or instead of writing b as a plus 2, you write 2n plus 3, 2n plus 3, 2n plus 1, and 2n plus 1. Okay, now you can solve it that way, but it just makes it a little bit tricky because we want to write the c in terms of a. And so if we left it as 2n plus 1 and 2n plus 3, it would work, but we would then have to rewrite it in terms of a, which makes it a little bit more difficult. So it's probably easier to leave them in terms of a so that we don't have to change that. Okay. So you can do that for achieved, get this far, or correctly simplify your fraction. So you might not have the right values here, but if you can correctly simplify the fraction that you have, you get achieved. If you can correctly expand the numerator, you can get achieved. If you can simplify the numerator, so you can get achieved. And if you have a valid statement derived from some algebraic grouping, you can get achieved. If you show a numerical proof, so if you sub numbers into this to show that you always end up with even over odd, you get no credit for that. So this is a generalization, a proof question. You need to be doing things in terms of a, and then having that explanation column. For merit, you need to do 3 of those things that I just achieved. And then for excellence, you get the correct statement, C with algebraic working, reducing to one fraction with the explanation. Okay. Cool. So the next question is from the 2016 paper. So there are 3 parts to this question, and we're going to go through all 3 parts, and that will finish us off for today. So we've got this triangle. Jason writes down 4 numbers, 1, 3, 5, and 7. Top of this triangle here, he adds the pairs of numbers to form a triangle as shown below. So 1 plus 3 is 4, 3 plus 5 is 8, 5 plus 7 is 12, and then you just keep going. So 4 and 8 is 12, 8 and 12 is 20, and then 12 and 20 is 32. Just keep adding as you go down the triangle. So he stops when he gets to this single number. Investigate what happens when Jason changes the order of the numbers in line 1. Does he get the same answer in line 2? So we just use the same 4 numbers, we're just going to write them in a different order. So you might move them all to the right one space. So if we do that, we would have 7, 1, 3, 5. 7 and 1 is 8, 1 and 3 is 4, 3 and 5 is 8, 8 and 4 is 12, and then we would get 24 as our number at the end, okay, which is different to 32. Or you might, so it says investigate what happens. So when it says investigate, you probably want to try more than one different thing. So this time we might put the outside numbers on the inside and the inside numbers on the outside. Okay, so if we do that, let's have 3, 1, 7, and 5. So 3 and 1 is 4, 1 and 7 is 8, and 7 and 5 is 12, 4 and 8 is 12, and 8 and 12 is 20, and 12 and 20 is 32. Okay, Cool. So we can see, investigate what happens. Does he get the same answer in line 4? Well, we know that he doesn't always get the same answer because in the first case we got 24. So no, Jason will not always get the same answer in line 4. Okay. So for this question, for achieved, 2 rearranged triangles are set up correctly. So you need to do 2 different things. Or 1 rearrangement and a correct statement. So if you rearranged to this and you only did this, you would need a statement that says no, that was different. If you did this and only this, then you would have a statement that says yes, they're the same. Okay. For merit, you need to do at least 2 different triangles set up, resulting in 2 different terminal or sort of numbers in line 4. Okay, and you need to have a statement that no, he's not always going to be the same thing. Okay, so that question only gets you to merit. We're just trialing different numbers. Okay, so this then continued. So we've still got the same triangle. It's now asking, find using algebra the relationship of the numbers in the first line to the numbers in the fourth line when he changes the orders of the numbers in line 1. Explain your answer. Okay. So it's asked us to use algebra. We want to find the relationship in the numbers in the first line and the numbers in the fourth line when he changes the order of the numbers. So let's just say that these are A, B, C, and D. Then we've got A plus B, B plus C, and C plus D. When we add these together, we get A, 2 B's, and a C, or we get B, 2 C's, and a D. So the one on the fourth line is 1A plus 3 B's plus 3 C's plus 1 D. Okay. So when he changes the order of the numbers in line 1, so because this is what we get in line 4, if we switched A and D around, we would still only have A and D. Okay, that'd just be the other way around. Okay, so switching the 2 end numbers will still result in the same terminal number, the same number in the fourth line. And likewise, if we switch B and C around, we're still going to end up with 3B and 3C. Okay, so switching the 2 middle numbers will also result in that same terminal number. Okay, so the number in line 4 remains the same if A and D swap or B and C swap in line 1. Okay, we get no change. So that's the relationship of the numbers that it's asking for, and this is explaining, that's the relationship, and this is the explanation that we're after. So for achieved, you get 1 general triangle. For merit, you have an incomplete explanation, or 2 triangles set up where the terminal number expressions are different, and you have some sort of partial explanation. Okay, for excellence, you give your explanation in general terms. Done here. That's a little bit more abstract, that question. Cool. So the third and final part of this question, still got the same setup for a triangle. If Jason writes 4 consecutive numbers in order, what do you know about the numbers if the number at the bottom of the triangle is divisible by 3? Explain your answer. Okay, so if Jason writes 4 consecutive numbers, so that's that consecutive term again, that means we have 4 numbers one after the other, 1, 2, 3, 4, or 7, 8, 9, 10. So instead of 1, 3, 5, and 7, we're going to have 4 consecutive numbers. So if we just say the first number is x, and the second number has to be 1 more than x, the third number has to be 2 more than x, and the fourth number has to be 3 more than x. Okay, so if we work this through, let's see what we get for that number in the fourth line, and then we can deal with this divisible by 3 part. So adding together, we would get 2x plus 1, we would get 2x plus 3, and we would get 2x plus 5. Adding these together, we get 4x plus 4 and 4x plus 8. And then 4x and 4x is 8x, and 8 and 4 is 12. So this is what we get. And we know that that's divisible by 3. So 8x plus 12 is divisible by 3. Well, we know that 12 is divisible by 3. Okay, it's the same thing as saying that 3 is a factor of 12. 12 is divisible by 3. Therefore, 8x must be divisible by 3. Okay, because we know that 8x plus 12 is divisible by 3. So that means that 8x would have to be divisible by 3. 8 is not divisible by 3. So, as 8 is not divisible by 3, x must be. Okay, so that means in line 1, the first consecutive number is divisible by 3. And coincidentally, because the last number is x plus 3, the fourth number, x plus 3, must also be divisible by 3. Okay, so if we just check that we've answered the question, what do you know about the numbers if the number at the bottom of the triangle is divisible by 3? Okay, so what do we know? We know that the first and the last consecutive number also have to be divisible by 3. So for this question, for achieved, you set up line 1 of your triangle using these general terms. You might use n's instead of x's, whatever variable you like, but they have to be consecutive. For merit, you get a partial explanation. And then for excellence, you have a full explanation. Okay, so maybe for merit, you note that 12 is divisible by 3 and 8x must be divisible by 3. But you don't go that next step and talk about the fact that x and x has to be divisible by 3. A full explanation, I don't believe you necessarily need this part here for excellence. You should certainly state that this x has to be a factor of 3 or divisible by 3. But you don't necessarily need to have this one in order to get that. But it's nice. Cool. Okay, so that's the last question that I have to work through today. Some of these questions are quite tough because they're so general, and you have to come up with expressions quite often based on that information and sort of work your way through. And you may not, when you start, necessarily know how things are going to fall out. So they are sometimes a little bit more challenging, these particular questions, but have a go. And as I've said before, if you try and it's not quite working, don't spend a huge amount of time on this. Go and solve some of the other questions that you might feel more comfortable with, and then you can come back and you might think of another way to sort of tackle it. Or you might come back and reread it and think of something else that you could try. So don't spend ages on these questions unless you've done everything else in the paper that you possibly can, and you're coming back to sort of finish it off. So tomorrow is the Thursday session, so the question and answer session. I have pulled out some questions from the 2011 and the 2012 paper to go through. Those papers aren't available on the NCEA website, so they may be questions that you haven't seen before. So I'll go through those, but if anyone does have any other questions that you've come across that you would like me to go through, then certainly either email me the question or take a photo and send me a message through the Facebook page. That would be fine, and I can go through those as well. But I thought it might be good to go through some questions that you might not have seen before. If you're not watching live tomorrow, then what you might want to do to get the most out of the learning opportunity from this is to have a look at the question, pause the video before I work through it, have a go at it yourself, and then if you get stuck, by all means, you can watch the explanation, or you can sort of skip through until I've got that full solution worked out there and see how you went. So that might be a good way to tackle the questions tomorrow if you are not watching live. If you are watching live, feel free to ask questions as I go through. If you get a little bit confused, or if I haven't explained something particularly well, just write a question and I can address that in here. Otherwise, yeah, this was my last sort of official lesson as such. Tomorrow will be the last Q&A. If you've got some feedback, I would love to hear it. So you can send me a message or an email, just a quick message, or just comment on the either the YouTube video or on the Facebook page on the link there. That would be awesome. As I said in the last video, I might potentially do these again for either tables, equations, and graphs, or geometric reasoning. But I just want to know that it's going to be useful before I put in the sort of time and effort to do that. So if you would like some videos for either of those papers, then please let me know, and I can start organising myself to get those ready. Have a great evening, and I hope you learned something from this video and that you get to watch the one that I do tomorrow, and that's helpful.